is the time. So how do we grow atomic layers? So you saw the deposition methods that are available. There are more, but you saw basically how they operate this on the basic perspective. So how do we grow atomic films? It's not trivial at all. So in this talk I will cover these two main members of this family. And I think that these are the two members that we can synthesize better, especially. So, but in general, when we deal with the methodologies to make these 2D materials, so one of the first ones, and many very, very popular, of course, is and everything started from that, is the mechanical exfoliation. Mechanical exfoliation, as I told you yesterday, you can do with the Scotch tape. And in the beginning, the test results were 10 micron, maybe 40 micron flake size, and very difficult to make of course, it's impossible to make conformal films. Now there are better methods. I think somebody asked me yesterday about that. I think that one of these papers is related to these methods of using a superficial metal layer in order to increase the size of the flake exfoliated mechanically from 3D crystals. Here you can see 3D crystals from mainly materials, in this case, thermal compounds or quality. Okay, but this is not good enough, of course, for thin films. This is not good enough for implementation of these materials into application. And sometimes it's not good enough in order to study the material on the long term. So then the second stage is basically the opposite one, is the liquid phase exfoliation. Why the opposite one? Because in this case you can get liters, a lot of material, but very small flake, very effective usually, and less suitable for high-end electronics. And the idea here is that you take again the 3D crystal, the same 3D crystals that I showed you before. You interpolate them with some compounds, and therefore, with many processing of sonication and many others, you can exfoliate them in solution. And that's why it's called liquid phase exfoliation. It's very popular. It is very good to obtain large quantities of material with small flake size. You can see here in the SE and 3M that you can use for a lot of things. Flexible electronics or composites, membranes, and so on. But if you want thin film, high quality electronic grade material, you must, I think, use one of these methodologies that we just saw. So I will be focusing mainly on CVD-based methodologies because these are the ones that are more accessible and also they lend the best results so far. But I will talk just a bit about that. So do you remember that I told you what I told you in the first talk yesterday? That this professor, very good software scientist, catalytic scientist, he did this experiment of exposing carbons to metal crystals at high temperature, and he observed the diffraction pattern that he thought is a reconstruction, new reconstruction. But later it was proved that these are few layers of graphite, they didn't call it graphene then, few layers of graphite on the metal. And basically, this very similar methodologies we use today, and we call them CBD chemical composition of graphene. So, as you remember, CBD means that we start from precursors that are volatile or gases, and we transfer them by a gas manifold to the reaction area, to the reactor. Now, from the precursor perspective, graphene is maybe the easiest one in CBD because there are many volatile liquid organic solvents that react as a precursor, and of course there are a lot of gases, hydrocarbons, that you can use to grow graphene. So, in the sense of precursor, graphene is maybe the best, the easiest for us for the growing process. And the system looks like a typical system would look like something like that, where you have a gas manifold system. Usually, you will be using the hydrocarbon for graphene. Methane currently is one of the best options. And one of the reasons for that might be that the thermal decomposition of methane occurs at a high temperature. That means, okay, we'll talk about that in a minute. And in addition to the hydrocarbon, you usually need some other gases, carrier gases, like inert gases, argon and hydrogen, and hydrogen, especially if you work in atmospheric pressure or low pressure, it's better to have some hydrogen present to react with any oxygen residue. Okay, so we have this. We have the system. It's a relatively simple system. Now, again, how the protein grows on metal and on metals. So basically, the process of CVD is a catalytic process, catalytic CVD. And that means that the hydrocarbon reaches the surface of the metal and decomposes catalytically on the surface. That's why methane is one of the best, because methane decomposes at high temperatures, and therefore the thermal decomposition, basically the non-catalytic decomposition of the methane in the reactor, is less than for other hydrocarbons. So let's start from nickel. Why from nickel? Because this is the type of metals that people in the 70s, like Somojai, worked. I showed you the work that he did on platinum, but many others after that did similar works on nickel surfaces. Now nickel, one of the things that you need to look when you synthesize a material is the phase diagram of the different components. In this case, carbon, which is the element that you need to produce graphene, of course, and the nickel, which is the catalytic substance. And you see from the phase diagram, so this is the carbon concentration increasing, temperature, and you see that in the phase diagram, you have a region in which you have relatively high dissolution of carbon into the nickel. Okay, so keep in mind that. You will see why I'm talking about this. So let's review the first case. Growth on metals with relatively high carbon solubility. Okay, so what happens? Is that you flow the hydrocarbon decomposes. So because of this solubility, high solubility, the hydrocarbon decomposes, the H2 flows away, the carbon diffuses into the metal. Okay? And then segregates out to form the graphite or the graphitic phase. Why it segregates out to form the graphitic phase? Because the graphitic phase is the most stable carbon crystalline phase. Okay? And that's why this mechanism leads usually to few layers of graphene, because the carbon first diffuses into the metal and then segregates out. And controlling the amount of carbon that you need for a single layer and to reach the kinetic considerations to reach a single layer on nickel is possible, but it's very, very hard. So that's why nickel or metals with relatively high solubility of carbon leads to a few layers of graphene and not single layer. Okay, so this is something that you need to keep in mind. So this is how it looks on a thick nickel. So you end up with tens of nanometers of thick graphene, which is basically a very thin graphite. Okay, this is how it looks on the surface. The reason that you get this, what we call wrinkles, basically it's like a paper that falls up, is because of the different thermal expansion coefficients between the graphite and the nickel. Right? We heat up the system, we heat up the nickel, we put inside the carbon segregates out to form the graphite, all this at 1000 degrees, and then we cool down. They have different expansions in coefficients.
So you want to say that the high catalytic solubility, the few layers will form.
Yes, in a metal that has high solubility of carbon, you will end up most probably with a few layers of graphene, because it's very hard to control the number of layers when you have high solubility.
So for making single layer, then we need to.
This is it, real quick. So, for example, if you take a look on the phase diagram, you see that the temperatures that are needed to grow high quality graphitic phase, which is usually between 800 and 1000, the solubility of the nickel is high. You may have another metal that the solubility, all this is shifted up to much higher temperatures, so then at the 1000 degrees, still the solubility is low. Higher temperatures, the solubility is high, so you need to check the solubility of the carbon at the raw temperature. That's what's important for you. Okay, so this is about growth on high solubility material. So what happens if you take now low solubility material? You have basically no carbon diffusion into the metal. So this is taken from the first paper on that, on 2009, by the Wu of in Austin, now it's in South Korea. And you can see here the phase diagram of the carbon atom. And you can see that basically at 1000 degrees, the solubility is 0.04. Two orders of magnitude lower. So therefore, you have basically no solubility, no diffusion into the metal. And then what happens is that the carbon again decomposes catalytically on the surface of the metal, but in this case it does not diffuse in, it stays on the surface. So the growth here is a surface mediated growth in contrast to the growth on nickel, that is a diffusion and segregation process. Okay, two different mechanisms for two metals that are a bit similar but leads to very different results. And how do we know that? Now we know everything, but how people knew that then? I mean, they could imagine that, but how did they prove that? They proved that by a very elegant way. The same group worked in 2010. Yeah, 2009. So what they did growth on nickel and copper, but they did it not with the standard methane gas that you can purchase everywhere. They did it with isotope enriched methane. So instead of having the standard isotopic concentration, I don't remember, but instead of having X C13, they had in this gas much larger. So they basically had a tank cylinder of CH4 which was enriched with C13 and another one was enriched with C12. And why is it important? How can you differentiate between that? And the reason is that when you grow graphene from the different methods, you can differentiate the peaks coming from the different graphitic materials that are formed by the different isotopes. And this is when you do a vibrational spectroscopy, like for example Raman spectroscopy. If you do Raman spectroscopy, the same characteristic peaks of graphene that we'll talk about that tomorrow will shift according to the isotopic composition. And that you can take from there because the mass changes and therefore the vibration slightly changes, but you can detect that in the one. And that means that if you grow like here a graphene with C12 and a graphene with C13 which method, you will get the same peaks but at different positions because the vibration will change. Okay? And now, how is that helpful? So they did this type of growth, they did this cycling. Do the growth for nickel, they took the nickel, they exposed it to methane high temperature. But in this case, they exposed the metal, let's say, to 5 minutes C13, then close it, and then 5 minutes C12. I don't remember the time, it doesn't matter. In cycles for each isotope. So after doing that on nickel, they did Raman map. So you can in Raman get a spectral, you can get a picture, you can get a mapping for the specific peaks on the surface. And you see that the map shows some homogeneous mix of the, in this case, of the signal from the isotope. So they couldn't differentiate anything. Now, when they did the same thing on copper, it is as schematically reproduced here. So first you expose the C13, so you create basically a lattice of morphine with C13 enriched isotopes. Then you continue with the C12, so you continue the growth, but this time with the C12. And then you repeat this process several times. They did the same process here, okay? Same here and here. But what happens in copper is that because the surface is, because the growth is surface mediated, so therefore you get, after doing the wonderful growth and the mapping, you get this beautiful flower. That the dark place here belongs most probably to the C13, and the bright area belongs to the C12. And this is because of the sequential growth. Now in nickel, you don't see that because everything diffuses in and then segregates out together. But on copper, because it's surface mediated, you can see that, and this is the proof that the growth mechanism on copper is completely different than the growth mechanism on nickel. And copper is surface mediated, or nickel is diffusion and segregation.
So it always forms in the curve shape, in the copper, on the copper.
Again, what?
If you take that shape, always in the copper, the shape that you show in the copper.
Yes.
So you always take that shape.
Well, the shape of the crystal depends depends on other factors. The shape of the pixel depends on the temperature, the pressure.
The reason behind the particular shape.
This is
shape.
This because of the symmetry of the. First, you have the same symmetry of the lattice of the graphene, and second, is this is most probably because it's done in low pressure. This mass limited growth. Okay. We will talk about that. Because we have no time for that.
So the G band is the difference between G and G dash band.
We'll talk about the one. Tomorrow we'll talk about the one. These are the most characteristic peaks of graphene materials. Graphene in particular. G and the G prime of the 2D, and the D, which here you don't see. The D refers to defects basically, and it's not here meaning that the materials of good quality. But anyway, this is not the point now. The point now is that by this elegant method of sequential growth with isotopes, you can elucidate the growth mechanism of different metals.
So one thing I just want to understand, in the first step, this surface segregation and precipitation.
Yes.
In the second step is absorption. In third step is absorption, again precipitation. So finally it is precipitation only.
Well.
The top of the ABC.
No, it's not precipitation. You continue the growth from the edge. It goes on and it's a lateral growth, surface growth, no diffusion, no segregation. Okay? Or not significant at least. Okay? Okay, now another interesting thing when we compare between the growth of the graphene and the catalytic metals and the growth of thin films, like the ones that I showed you before, is that if you look at the thin film, the interaction, of course, with the substrate is covalent, ionic, or metallic, depending on the metallics on the fuel system. And when you have, the new atom on the surface, it will surface, diffuse till it reaches the preferred site, which is in this case the kink. And this is, and the energy that it needs to pay for the incorporation is not high. It's just the energy of the popping from side to side, similar to what we saw before. But in the case of graphene, it's extremely different. As you can see here, graphene, so this is the graphene edge on, in this case, copper. Okay? Now, the graphene itself, the interaction with the substrate is weak. It's van der Waals interaction. Okay? But the edges of the graphene are strongly bonded to the metal. Actually, this bond is very strong, few electrons, it's very strong. So in the beginning of the research of the growth of the graphene, people asked how it is that a single atom of carbon diffusing on the substrate reaches the edge, and where the energy in order to break these bonds and then these bonds and generate the new bond comes from. The thermal energy cannot account for that. So how the graphene grows? You understand the problem? The process of the atom incorporation into the graphene edge theoretically is too high. It cannot happen. So according to the calculations, you should not grow graphene on top of the copper as in the surface mediated growth. So the answer to that came from two theoretical groups, one from Rice, the other one from National Lab, Zambia, where they say, basically they say the same, different numbers, but they say the same. And they say, okay, this cannot happen. You don't have growth by incorporation of single atoms to the edges. What you need to have in order to have incorporation is a small cluster here, small cluster of atoms. And then it will be energetically favorable to break these bonds. And what's the size of the cluster? So that's the difference between the two groups. I remember one saying 5, the other one saying 9. So I don't know what is the truth. I guess that it differs on the crystal plane and it differs on depending on the other parameters. But this is the main principle, and this is what's also very different from the growth of other substrates. Now another difference is that the best growth of graphene on top of copper is obtained at temperatures that are very close to the melting temperature of the copper. The melting temperature of the copper is 1086, something like that, while the growth of graphene on copper, the best growth is between 1000 and 1050. That means that the surface of the copper is probably melted. And the diffusion, that's why the diffusion is so high. The mobility of the atoms on the surface is so high. That's why copper works very good. In contrast to other metals that have also low solubility of carbon, still copper works best. So it's not, the solubility is one of the needs. There are many other parameters that influence the growth as well. So here we list a few differences when we compare the graphene growth and the growth of the filters. So the growth of graphene is reversible, meaning that we are flowing the CH4, the methane. If we stop the methane, the graphene will be etched away. Will be catalytically etched away. Okay? But if we grow a thin film and we stop the precursors, like gallium arsenide, whatever, we stop the precursors, the film will not be etched. You may generate defects, but it will not etch. So this is a difference.
So the crystal structure of the substrate also matters for the graphene growth. There's COX. So
first of all, you need a transition metal, catalytic metal. Second of all, if you want single layer, you need a metal with low solubility. Third of all, if you want good results, you need a metal like copper that has melted surface and diffuses high diffusivity. Third of all, purity, surface roughness, and a lot of other things.
So the preferable crystal structure of the graphene or the preferable crystal structure.
We'll talk about a few words about epitaxial growth. You can grow epitaxial graphene on 111 copper very well. So epitaxial graphene meaning that it's mostly single crystal.
So 111 plane is preferable.
Yes. For epitaxial, it's
For CVM also.
well, if it grows epitaxial, it's the best result that we can get. Right? Single crystal all over. Yeah, and also the interaction between the ground layer and the crystal is completely different. The graphene interacts very weakly, while any other field will interact strongly, especially the epitaxial group. So you have chemical bonds. So this is the differences. But due to all the research, knowledge, this is from a few years ago. 1 centimeter single crystal graphene. Nowadays we can grow, it is possible, this was done in my lab, you can grow single layer of graphene on, or very close to single layer, you have defects. A single layer graphene on top of copper 111. So this is a case where we prepared copper 111 on top of a sapphire. So first you grow epitaxially the catalytic metal, and then you grow the material, and you're seeing that the metal is epitaxial with the sapphire because of the directions of the metal, but it is different. So it is possible not only to grow very large crystals, centimeters nowadays, but also to grow epitaxial crystals, which is even more than 1 centimeter. And there are even, I told you yesterday about these two companies. So they do the growth on wafer scale, on wafers. But there are other companies like this one, General Graphene Corporation, in which they grow on what is called wall-to-wall CVD. Do you know what is wall-to-wall? Do you know what are films? Anybody here took pictures with the films? Not the electron cameras? Film. You know what is a film?
Yes, sir.
So the films were made by wall-to-wall processing, right? So you have the initial film and you roll it from process to process. You have a lot of stations. Here you deposit another material. Here you anneal it. Here everything by rolling it from side to side. So therefore you can process a lot of material. And the same this company is doing, or similar this company is doing with the graphene. What you can see here is the idea that the nickel before entering the growth strike a big strike of nickel. So you can grow by this method, even if we don't understand 100%, you can grow very large, high quality and large scale single layer graphene on top of the
And what is the typical cost of growing graphene? Typical cost. What is the cost of
cost? Research lab, we don't know how much it is every experiment. You know how much is the copper. It's relatively cheap. It's not so expensive. But when you compare it to exfoliated graphene, it's very expensive. That's what you need. Okay, but now we have the graphene on the metal. So what do we do with it? In order to study it, in order to make devices, in order to do whatever we want to do, we need to transfer it. So one of the most known methodologies is what is called the wet transfer. The wet transfer, you have after the growth the graphene on the metal and the copper and the other metals. Then you spin coat this substrate with a polymer, usually TMDs, in order to provide some mechanical support. Remember that we are talking about single layers, single atomic layers. Then you etch with the wet etchant the metal away. You etch the metal, and you remain with a polymer filled with the graphene on the bottom. And then you transfer that to the target substrate. After that, you need to etch to dissolve the polymer, and that's it. You get the graphene. So the problem with all this process, of course, is contamination time, but it works fairly good.
So, can we use any other polymer?
Yes.
As in the case of SML?
You can use a lot of polymers. There are a lot of reports about transferring graphene, and there are also reports of transferring graphene by dry metals. So for example, with the thermal release tapes. That's another method. So basically, thermal tapes that you stick the graphene to the thermal tape, you take it away without, even before this step, you fill it away, and then you put it on the substrate, and basically you heat it up in order to release the tape. This tape is adhesive at low temperatures. When you heat it up above the threshold temperature, the tape, the adhesion weakens, so you can take it out. And you need to clean it, of course. So there are wet and dry methods.
What is the best method for coating?
Sorry?
Best method for coating. What is the best method?
Best method, the easiest method is spin coating.
So, is it sufficient or you need any very good controllable?
You don't need a controllable field. This is only for the PMMA here is for support. You're very flexible. And another few words about another method to grow wonderful graphene. And the story about this method is that the first paper that they reported on this method and reported also similar electrical measurements that Novosel and Gain did in 2004 was also published in 2004. Both papers, actually there was another paper also from PhD in New York. Three papers basically reporting the electrical properties of graphene. But the unique thing about this paper was that the other two papers were done by mechanical exfoliation of graphene, and this one was done on chrome graphene, single crystal graphene, on top of silicon carbide. So this is the method that I will briefly, in a few words, describe. So, to go by CVD, we know that we need to provide the carbon by the precursor, and then react it on the metal. And in this case, we don't need any precursor. In this case, the starting material is a silicon carbide. Okay, ceramic, very high thermal melting temperature. That what happens is that when you heat it up in vacuum, when you heat it up at a high temperatures above 1800 degrees, close to 2000, even a bit more better, what happens is that the silicon selectively evaporates out, sublimates out from the silicon carbide, leaving the carbon behind. This carbon, at high temperatures, again, forms the graphitic material. Now you may ask, so why here the graphene is formed at a non-catalytic substrate? Because silicon carbide is not a catalytic substrate. But in CVD, we need a catalytic substrate. And the straight answer is the temperature. So I'm not sure if you're familiar with what is called a highly oriented pyrolytic graphite. Highly oriented pyrolytic graphite is the best synthetic graphite available. And it is done by putting a carbon precursor, solid carbon precursor, in a chamber in which we can apply gigapascal pressures and heat it up to about 3000 degrees. Okay? And in that form, a very good quality graphite is grown. In this case, we don't reach 3000, but the amount of carbon here is not great. So what happens is that the graphene grows epitaxially with the silicon carbide. And then it depends what side of the silicon carbide you use, because If you use the carbon terminated phase, you get a multi-layer. If you use a silicon terminated phase, you get a much thinner, probably sometimes a single layer. And but this is also a very interesting approach. But of course, you need very high temperatures like okay. Questions for graphene growth? So now let's move on to the growth of
So in the previous slide, so here for making this immediate graphene, so initially you have a substrate of silicon carbide of very very thin.
No, thin carbon is a bulk. I mean, a wafer.
So how much time you keep on removing the silicon and how much time you make the carbon simulator? So again, first of all, you just remove the silicon only in the top layer and then you peel the carbon layer from there. Is that right?
Yes, you can do that. Also, you can use also the silicon carbide to build the devices. You can build your devices with the silicon carbide.
Directly on the
Okay. Okay, so let's start by. So we know the basic to grow graphene. Now we need to grow other materials. And in this case, TMD, transition metal hydrogens. So one of the easiest ways to start to grow these materials is by the reaction of metals with the hydrogen elements. Could be sulfur, selenium, or even aluminum. For example, as you can see, these schematics. So what we have here is a foil of a metal or a thin film of a metal that we can react with, in this case, sulfur, but you can do the same with the selenium. And what happens is that you convert the metal reacts with the hydrogen. If you use, of course, tungsten molybdenum, so you get the famous molybdenum tungsten selenide. And therefore, this is a very easy process to do. As you will see in a minute, the results are not like you see these days. So what happens here is that we are taking a metal and converting it into a completely different phase by reaction. In this case, a phase with a different volume, a larger volume, so we have a volume expansion. And as a result of that, when the thin film of metal is thicker than, say, a certain number, depending on the material, usually few nanometers, the TMD material will grow perpendicular to the surface. When you have a very thin metal, you will grow it preferentially planar. And what's the problem with that is that depositing thin films with very thin, with the thickness small as few nanometers is very hard. PVD, all this metal is very hard to deposit thin films like on these thicknesses. So usually by this method, you end up with 10 nanometers in continuous. And therefore, you end up with the vertical growth, as you can see in this TM pictures. So again, as you can see now, work in this TM picture. So this is a TM taken from in plane. Basically, we take this vertically aligned MOS2. We transfer it to the TM grid, and we take a look from the top. So basically, you see the standing, all these lines are the standing layers, okay? But if you take a cross section and you take a look again in the TM, you will see again the standing layers on top of the silicon dioxide. Okay? And for example, you can use this for, and you can also do fairly easy heterostructures. You can take two metals and sulfurize them or halogenize them in the same reactor. And depending on the temperature of the processing, you can achieve an alloy of the metals and then an alloy of the TMD, or to get to the different phases, the molybdenum phase, the molybdenum decelenide, and the tungsten decelenide. So you can get both depending on the conditions of the sulfurization, the coordination.
So this is first you are making the sulfur and you are making first at a time. WH2, MH2.
I'm flowing this. Again, what's the question?
So the purpose of this is using like tungsten and molybdenum.
Yes.
It is to make the infrastructure, right?
Yes, for example. Yes. Or a structure or an alloy. If you do it at very high temperature, the molybdenum and tungsten mix each other, and then you make an alloy.
So suppose you have a controlled temperature, if you want to make infrastructure.
Yeah, you can.
So what is the
Here you see some images. These squares that you see here is tungsten disulfide. And the substrate, continuous substrate underneath is molybdenum disulfide. For example.
molybdenum sulfur in the top, right?
No, at the bottom. But it doesn't matter, you can change it. In this case, we did it in the opposite, okay? Okay. Yeah. So we did some erasers for that, that can operate at high temperature. Okay, but these materials, of course, this is nice for a lot of applications, might be nice for a lot of applications in studies, but this is a method that gives you basically a bulk material. So if we want to take advantage of the single layer material, so the optical properties, the photoluminescence that we discussed yesterday, and so on, we need a method to grow single layer material. And that happened. Okay, that was proved for the first time around 2012. So you remember, graphene was grown for the first time in 2009. This material was too first time in 2012. If I remember right, I don't see the citation here. Probably it's underneath the other right hand. Anyway, that was of course very nice. And since then, many groups, of course, are going by the same method. What they did is, as I told you before, in CVD, you need to choose the precursor. So what they took as precursors is for the metal oxide, MO3, and for the halogen elemental sulfur. They just put it in the surface, in the reactor, heat it up, and they got some results. Now, what's the problem with these precursors? In particular, with this precursor. This precursor, in contrast to what is needed in CPT, this precursor is non-volatile, has very low vapor pressure. So that means that you need to heat it up at least to, I don't know, 600 or 650 degrees in order to get significant evaporation and sublimation for it to react and grow the layer. And that's a problem. Why is it a problem? Because then you need to put the precursor inside the reactor by the sample, because the growth is done at very close temperatures. And that's a problem, right? Because in contrast to the typical CVD processes in which you deliver the gas from the outside, in this case you need to put it inside the proposal. And the problem with that is that we don't have, or we have very little control over the flux of the metal to the reaction. And therefore, it has a lot of problems, as you will see in the next slides. So here, for example, you can see again CVD with the same metal oxide and also can be olefin oxide or tungsten oxide. Tungsten oxide is even a bit worse because you need to heat it up to higher temperatures to get a significant evaporation. And what happens is that what happens is that in general, if you don't do any treatment, the outcome of such growth will be distance related. The impact on the distance will be high because of the diffusion, right? So you will have areas with high flux of the metal, and therefore you will have multi-layer structures, even standing flake structures. And then you will have also some areas with very thin layer formation, even atomic layers, in this case 3 atom thick. But it is kind of non-controllable. Further than that,
the biggest just want to understand the process. The above figure. So sulfur, you are heating it 150 to 300 degrees centigrade. And you are just making it evaporate in the carbon dioxide. And then the molecule, you are maintaining about 500 to 900 degrees centigrade. So
this one is about in between, let's say 600 and 900.
so both the temperatures are different.
Yeah, that's why the sulfur and selenium are upstream. Upstream meaning before the gas reaches the substrate. Here is the gas manifold, argon, hydrogen, and everything that you flow. You flow it through the hydrogen, and then it delivers it to the substrate. These ones sublimate and evaporate at relatively low temperatures, between 150 and 300. So you don't need to put them inside nearby the sample. But this reactor, these precursors, you must have them near the surface. Otherwise, you're not going to surface.
But we need to mix molybdenum and sulfate, right? We need to combine it. How do you combine it? Because
the gas comes from this side, right?
Mm.
And delivers the sulfuration. In addition, you have a vacuum, so you have a flow in this direction.
So it will automatically get the sulfur from the chamber to other chamber.
It's not another chamber, it's the same reactor.
Same reactor.
But it's a tube reactor, just two different areas. Two heating areas.
It will take from that portion to this portion. The gas.
Yes, the gas flows. So, so by doing this, not only that it's not uniform, but depending on the evaporation of the metal oxide, you may get very interesting structures on the surface before the reaction with the hydrogen. So in that case, you're not going to end with atomic films. You're going to end with all kind of different nanomaterials, very interesting materials, but not atomic fields. For example, in some conditions you may reach the place in which you may, before the growth, nanoparticles of metal oxide are grown on the surface. So that means that not enough that too much flux of the metal was reaching the substrate before the sulfur arrived. Therefore, the metal oxide is formed before the reaction with the sulfur. And then once the metal oxide is formed, it starts reacting with the sulfur according to the mechanism for the inorganic fullerenes growth. Are you familiar with the inorganic fullerenes? No. So there are the fullerenes, which are carbon nanoparticles like the C60 that I showed you yesterday. This soccer ball made of 60 atoms of the carbon. But there are also inorganic fullerenes from all these TMDs, NO2, tungsten disulfide, basically small particles. They are not entirely circular, spherical, but they are particles, and they are formed in a totally different way than the carbon ones. In this case, you need first a nanoparticle of metal oxide, and when you sulfurize this, it starts the sulfurization from the edges and it moves inwards till all the metal oxide is reacted, and you end up with a hollow inorganic fullerene. This is how it looks, an inorganic fullerene. It's similar to the C60, but different structure and usually multi-layered. Now, if you do it in different conditions, you end up with different crystals. But then the reaction is the same. You have the metal oxide nanocrystal that it sulfurizes from the edge, like in these schematics. And finally, you can have an interstructure with the metal oxide and the TMD, or you can have only the TMD. Or you can reach the right conditions to achieve relatively large areas of atomic fields. You can do also that, depending very much on the metal flux, on the ratio between the metal flux and the hydrogen flux. Now, in order to solve that issue, the issue of the flux of the metal that is very hard to control, there are many groups that came up with some solution. One of them, for example, you can see here, where in this case you can grow, for example, in 16 parameters that with a high flux of metals, you get a lot of flux to the metal. But it doesn't matter because the area of that we are interested to grow is the area that is confined between, in this case, silicon and mica. So this is only in this area we want to grow the atomic layers. The other areas we don't care. We can isolate. Okay, so this is a way in which you don't care basically about the enormous fluxes or non-controllable fluxes of the metal to the surface, but you ensure that you can reduce the diffusion of this of the metal precursor by this confinement. As you see here, schematics of the carbon concentration on the substrate as a function of X. So therefore, if you do it right, like my Indian postdoc did, or not my partner, so then you can get very nice results. Another method in order to control the crystallinity, to improve the quality, and to control also the monolayer sometimes, is what we call seeded growth. So seeded growth is very famous, as Professor Kumar mentioned before, in 3D crystals. You can see here this smiling guy is, you see these crystals? These are single crystal semiconductor crystals, I think they are silicon. This is small compared to the industry can do today. Today we can grow huge crystals. All single crystal, all the atoms aligned like soldiers, okay? And all these I don't know if you're familiar with the Chobrovsky method, but all this starts from a crossable, a huge crossable with melted silicon, for example. And then what you do is you come with a seed, a tiny crystal of silicon with the crystal orientation that you want to grow in these ingots, and you put it in touch with the bed, and then you pull it very slowly. It's a process that was improved over the tens of years, over the decades ago, but it works really, really good for 3D crystals. So then our question was, so how you can improve the seeded growth for 2D material? By the way, seeded growth also is very popular in colloidal growth, where you grow nanoparticles in solution, right? You put some seeds, and here is, by that you control the nucleation step, the nucleation, and then the growth steps. So you can do the seeded growth in order to control to increase the domain size, to control the domain size, as you can see here. So what people did, and also we, is we use seeds, in this case of metals, that you can pattern with different pitches, different distances between them, and therefore allowing for crystal growth of a different size. For example, in this case, you see that the distance is small enough in order for the crystals that nucleated at the crystals, at the seeds, merge together. But in this case, not only that they are a bit too far away, but sometimes you may have also some nucleation that seems to be not related to the seeds. And the idea of the seeds is that we didn't talk about nucleation in the last step because we have no time, but basically when you grow a material, right, you need a certain amount of material, and you need a stable nucleus to be formed, right? In the beginning, the energy is not favorable for the material to grow. The material in the beginning grows, needs to reach the stable phase, and then continue to grow. So it nucleates and then continue to grow. And so in this type of growth, it's very important to be in a stage in which you need to ensure that the nucleation of the material that we are growing occurs only at the seeds and not in the center. And for that, you need to reduce the distance between the seeds, so then you ensure that they are long enough in order to allow for big crystals to form, but not too long, because not much longer than the surface diffusion length that we talked about that in the last session. Because if the surface diffusion length is very short, then you have high probabilities that you will get nucleation in the beginning, in the middle, not only of the seeds. Therefore, you cannot do the seeded growth by that. So this is a general form to try and improve the quality, the crystal size, and also location of these domains. But, as I told you before, the CVD-related methods using the metal oxide precursors are not suitable. Metal oxide precursors are not very suitable for CVD. Therefore, you need to place them in the reactor. They have a lot of problems that they just mentioned. So, therefore, one option is to move to a volatile precursors. Okay? Volatile precursors, like the precursors, type of precursors that I talked the last session. Metal organic, for example, or metal halides, metal chlorides. These compounds have relatively pressures, high vapor pressures, and therefore can be used in a suitable manner in CVD. And what is a suitable manner? A suitable manner is a way in which you take out all the precursors from the reactor. So the reactor is clean, only the growth substrate, and that's it. And therefore, you ensure by that you can control in a more precise way the precursors class. So yeah, if you use metal organics, it's metal organic CVD, metal halides like metal chlorides and metal halides. So indeed, when you do metal organic work, when you do metal organic work, is indeed a method that is much easier to deliver the different processes, but you may have other problems, like different impurities, contamination that arises from the precursor. For example, carbon, which is a detrimental contamination, right? We don't like carbon in semiconductors in general, and we don't like carbon on the surface of the globe because the carbon contamination will act by itself as a nucleation point. And as a result, we'll get a density, too large density of nucleation, and therefore you will end up with a nanocrystalline film with very low properties. Okay? You see here is a continuous films, but nanoscale crystallinity, nanocrystalline film. So there are several ways to improve that by doing the MOCVD. So MOCVD is still promising. There are ways to get rid of the impurities by, for example, controlling the flux of the hydrogen. Hydrogen reacts with carbon, forming hydrocarbons, so therefore gasificating the impurities, and also by introducing very small amounts and for a very short period of time of oxygen or water vapors. The water vapors will react, the oxygen will react with the carbon leading to CO2, therefore cleaning the surface from the carbon. Now, but still, in MOCVD, you get very small domains, and is the problem to obtain high quality, high crystalline materials. So therefore, one of the ways to do that, like in semiconductors, is to grow these materials epitaxially on top of the substrate, right? In principle, if you epitaxial layers, it doesn't matter that the domains at the beginning are very small, as long as all of them are oriented and in the right orientation, they will all merge together to a single crystal. So that's the idea of epitaxial growth, right? Now, when we talk about a conventional epitaxial growth, like we discussed the last session from, let's say, 3D crystal and 3D. So again, you have a bonding between the substrate and the epilayer. You have a covalent, covalent metallic, the ionic materials, but strong bonding you have between the layer and the substrate. But when we talk about van der Waals crystals, van der Waals materials, as you see here schematically, we don't have that bonding. We have a van der Waals interface, right? We have a weak bonding between the 2D and the 2D, and then it will be van der Waals epitaxy. If we grow 2D on top of a 3D substrate, we will grow it by, it will call a quasi van der Waals epitaxy. And these terms were coined by Kumo in the 80s, in the 90s of the last century. He noticed that when he grew some materials, some 2D materials on top of other 2D materials, and they had very large mismatch. You remember the mismatch, the difference in lattice parameter, which is one of the crucial parameters in order that dictates if we can grow epitaxial or not. Even for large mismatches, he could observe epitaxial growth. So he explained that in the sense that since we don't have here strong bonding, we don't have the strong limitation of the lattice mismatch that we have in 3D crystals, because this weak bonding allows for a surface relaxation, right? And so then we don't have the same lattice mismatch problems, right? When we have a strong lattice mismatch, the problem is that a lot of defects are created, and then a lot of things can happen. But in this case, we don't have that. Yes?
Will there be any nucleation in this case?
Sorry?
Will there be any nucleation in this case, or how will it be decided? Because there is no connection between the grade substrate and
You're talking about nucleation, so how the nucleation takes place? That's a very good question. That's a very good question. How the nucleation takes place on a van der Waals material? We talked yesterday about that the 2D materials have no dangling bonds. And that's why even in ALD, it's very difficult to make a thin layer, conformal layer on top of that. So how we can nucleate another 2D materials? That's a very good question. I must say that I'm still trying to answer that. I think today that what happens is that in order to grow, not only epitaxial, in order to grow on a 2D material, in my opinion, you need a defect. You need a defect to anchor the first nucleation stages. And then the material could align or not with the substrate, with the 2D substrate. But in my opinion, and we see that in many experiments, that you need these defects to act as the anchor point for the first layer.
Say that we go with the discussing. So basically, if that could be the reason, then let's say if we can take two layers, one maybe by the exfoliation and another maybe by the CVD ground. Usually exfoliation material has less defect than the CVD ground material.
Yes.
And then if you grow the second layer over board, and then if you find that yes, on the CVD layer we can easily grow the second layer rather than the exfoliated one, then we can grow this.
So we did that. That's why I'm saying
Oh,
that
you
I'm
did?
pretty
Okay.
confident. We didn't publish yet, but we did that.
Oh, you did? Okay.
So we did the low temperature epitaxial growth
Ah.
by doing that on CVD grown material. And when we compared with exfoliated, we didn't get any growth.
Okay.
So there are indications
Oh,
that
yeah,
it
yeah.
is true, but it needed still need more.
Sir, whatever 2D substrate is, 2D substrate means it's already a 2D material substrate.
Again, what?
What is the type of 2D substrate you mentioned there?
2D substance is any 2D substance. Graphene, MS2,
yeah.
Selenide, whatever.
So what is the typical thing in the substrate?
For the theoretical discussion of the van der Waals epitaxy, it doesn't matter. It doesn't matter. Okay, so then he saw that you you get epitaxial growth even in large mismatches, right? Because this is strain relaxation. But actually, the truth is more complicated, and the truth is that even an epitaxial growth on large mismatches, with large mismatch, the system aligns itself along a way to try, as an attempt to try and reduce the lattice mismatch. For example, in the TMD on sapphire regime, I think, and hope that I'm not mistaken, I think that 3 lattices parameters align along 2 of the sapphire, or the opposite. So therefore, and that, if that happens in conventional semiconductors, it will create a lot of defects. TMDs, it does not. So this is one of the advantages of having a epitaxial group with the TMDs. Here you can see the first paper, not the first paper here on the left from a Stitch group. And here you can see a lot of papers from the Penn State group, which are the leading ones on the epitaxial group and MOCPD group. And this is so this is what kind of the results that were obtained by several groups, including mine, where you can see that the triangular domains, in this case tungsten disulfide, are all aligned, but some of them are aligned up and some of them down. Now this is a problem, assuming that these fields should coalesce together and form a continuous single crystal field. So when you have these 2 rotated crystals, is a problem because they will make line defects. And this happens, of course, because of the surface of the sapphire. So there are a few recent papers showing that they can overcome this methodology by different methods. Some of them use a different plane, sapphire plane, some of them use other modifications, but in this case, a very recent paper, very nice paper, they showed that they modified the paper with the sapphire. The sapphire is a single crystal aluminum. They modified the surface with the atomic layer of lanthanum, and that breaks the symmetry of the sapphire, so it's orientation only along one direction. By the way, in our paper, we show that we can modify the surface of the alumina, the sapphire, with an atomic layer of tungsten. So they did similar with lanthanum. Anyway, interesting. And yeah. Questions so far? So lastly, a few words about ALD. I told you, ALD atomic layer deposition should be the best way to deposit atomic layers. But it's not. And it's not because, you remember the characteristic diagram of the ALD deposition, or the growth mechanism. So you have the parameter window, temperature window, right? So you have a temperature window, very specific one to get the ALD. Above that, you get many other processes that are not ALD and are not wanted. And this process range is quite low temperature. It told you something about 200 to 450. This is considered low temperature for crystalline thin film growth. And that's the main reason that ALD growth of the TMDs, and it is done, it's not that people haven't tried. For trying, you can grow, of course, this the crystallinity will be rather low, and also actually in atomic layer deposition it's very hard to control the atomic layer number. I didn't see any result in ALD showing a single layer formation. And here we can see an example in which, and usually after the ALD, in order to improve the crystallinity of the layer, you need to do some annealing process. Okay, so here we can do a nice grown film, which is mostly amorphous. And this is the same film after this cross-section PM, of course. This is the same film after annealing, usually in the presence of sulfur. Okay, so you anneal sometimes at higher temperatures than the ALD growth process. And then you can improve the crystallinity of the layer, but still, as you see, you cannot grow. I don't know of any result that's growing single layers, and the crystallinity is quite low.
So in ALD, you said earlier, so once at a time we send only one precursor, right? So if you have a like
When
in the normal section
with the
ALD, not like ALD you said, we send
you need two proposals. You always need two proposals.
but at a time we send one precursor, right?
In ALG,
ALD.
this time,
Not just in the beginning, the morning section you said, at a time you send one precursor.
ALD I said always two proposals.
But one after the other, right?
Yeah,
One after
because-
the other.
yeah.
That's it. So one after the other. When you send one precursor at a time, it's found on the air. So when you send another precursor, will it go and attach on the top, or it will react and it will come and suppose it like molecule and sulfate.
So you basically are asking if ALD performance 2, for example, is real ALD. Right? How ALD of the TMD should work? First the sulfur layer, then the metal, and then the sulfur. I don't know yet, but I don't think that you can roll like that, right?
Yes, sir. So suppose as we showed that table, right? In the earlier, showed on the table.
Yeah.
So in that table we have a several substrate. So you see, so there are two precursors who are going on a particular substrate, right? So in this case, so in this case you are developing a component, like you are sending one precursor A and one precursor B, and they are going on a substrate, right? So what the materials are ultimately like only TMD material in this table what we want to do.
I'm not sure that I understood this question. Yes, these recipes were reported for the growth of M2 or tungsten, and the sulfur.
Yes, sir. So it is growth of emulsion MOC2 on the substrate to ALD process.
Yeah.
So in this case, when you send one precursor at a time, like one after the other, so the formation of MOH2 is because of the reaction between the two layers, two precursors, one after the other, or it's a combined process.
What do you mean combined process?
I mean, you are sending one precursor at a time. Once you are sending one precursor and you are sending.
So you have molybdenum precursors, molybdenum atoms on the surface. You expose it to sulfur, it will react with the sulfur. But you're right. I don't think that it's not an atomic layer deposition growth mechanism as we saw before for the aluminum oxide.
Yes, sir.
It cannot be like that, in my opinion.
So, what is the difference?
Well, the difference is that there you modify the upper surface with one of the precursors. And here, and the final result is an amorphous aluminum. Here you want to do something crystalline that is layered. I just don't know how. I mean, the only method is by depositing by ALD and having and getting some nanocrystalline amorphous molybdenum sulfide, and then annealing it to form the layer that is not crystalline structure. Yeah, if you anneal it in the right conditions, you will get some crystalline materials.
So in pure, it has some, it's pure crystalline, or it has some.
You can take a look. If you look at the cross section, I showed you yesterday, cross section of the 2D materials that were made by MB, they look completely different. In MB, you see the big crystals, all the lines are lined like solid. And here you see that they are not so aligned, you have a lot of defects.
So it's amorphous only.
Is what?
You are amorphous.
This is not amorphous. Amorphous is the small, the left one.
No, sir, these that are in the water,
A is grown and B and D, the amorphous and layer, respectively. Other questions?